Great. And hello again, especially for the people who watch the recording. Okay, so today our first class on fundamentals of robotics. That course traditionally is sort of an introduction to that serves as a background for a series of other courses. Pretty much everything related directly to robotics later will somehow build on top of this course. So here our main concern is to give you the background, all right? So in a sense, while it says introduction, a lot of the material which we'll cover here would be complete, as in you don't have to take like robotics 2, robotics 3, to actually have the knowledge that is immediately useful. Like what we are giving you here will be immediately applicable, useful, etc. So in this sense, please don't treat this course as just a, some first step towards something. Is in a sense it is complete information that you will need. All right. Before we can proceed, I think we need to, since this might for all in all be your first attempt to think about robotics, I think it is fair to answer or ask the question what robotics even is, right? And I think you probably thought about it before, right? Like what is robotics? So like when I was studying, I think one of the attempts that people used to answer what robotics is was to say is a combination of mechanics, electronics, sensors, software, this kind of stuff, right? I think right now there's a popular tripart combination, something like sense, act, something else, right? Those things show up every now and then. Back when I was studying, there was also a popular topic of mechatronics, which was like a synergy, or like the same thing, but with a synergy put in, as in you get more out than you put in. Those attempts are interesting. They define basically components of the science that you study. However, for you as Innopolis students, you look at this and you say, okay, mechanics, that is not what I study very rigorously. You had theoretical mechanics, and I think that is the last course of mechanics that you study. You're not going to study something like, I don't know, maybe you are going to study something like design of machines, etc., like those typical mechanical engineering courses. Electronics, I'm not sure if you have even one course on that. Sensors, I think you have 1 or 2 courses, but pretty much all your courses are related to software. So you can see you have a huge bias in one direction, but that does not make it less robotics what you study, right? So in a sense, this definition is interesting, but I think it does not reflect real life. Like in real life, that is not how robotics the word is being used. But it's definitely a useful combination to keep in mind, a useful definition. All right. Another definition, which is kind of like not from components, but from the results, is that robotics is somehow a study of machines that make decisions based on data about real world. Okay. So, for example, a drone that flies around a building would be a robot. Why? Because it corrects its own flight using data it acquires during flight. And you give it higher level commands, kind of like fly from here to here to here to here, and it decides how exactly it's going to do it, right? And you cannot know in advance how it's going to do it, because it depends on the world condition. Whereas simple automation, like pick and place operations in industrial settings, where they pick something, place it elsewhere, someone drills a couple holes, something else happens elsewhere. That is not robotics, that is automation. Like, for example, production of screws is automation. whereas a robot vacuum cleaner is a robot. That is a difference. So this definition is useful for trying to understand where robotics stops and traditional mechanical engineering and automation starts. Because as you can imagine, something like a washing machine is already quite automated. And you cannot allow the term robotics to expand indefinitely into everything that is automated. Like, my water heater has a switch that automatically makes it stop boiling water when it is, about 100 degrees. So somehow this, you can construe it as being a robot, but we don't want to call it a robot. We want robotics to be defined narrowly enough to be useful. Okay. So the second definition just aims at cutting off stuff that is not really robotics. Okay. If you have like opinions about that, now is a good time to give them. That is usually the kind of stuff that people have strong views about, like what is a robot, what is not a robot.
So, did you understand correctly that, for example, manipulator on this factory is actually not a robotics, but more about automation?
Yeah, that is a very good question. That's a very good question. So if you use the second definition, manipulator would be, I think, would be still a robot, because it corrects, it's like somehow corrects itself based on environment. But that is kind of my take on it, because like it has this feedback control system, and ultimately it a lot of work done with controlling, with manipulators making them work, is making sure that this control system somehow performs correctly, right? So what I'm trying to say is, if you give manipulator just some input without being very careful about how its control system is going to operate, it's going to go wild. That is a problem. So you have to first design a control system that makes it take inputs about what's going on. In this case, just internal states, and correct its torque inputs. That is how I would read it. But I agree 100% that this case is borderline, because somehow it is a repetitive motion, usually, with manipulators. I think some other people would say that it is reprogrammable, as in you can program it to do different stuff, and that makes it a robot, whereas something else is not reprogrammable, so it's not a robot. But there, we run into a problem that 3D printers are reprogrammable, but we do not consider them robots usually. You understand, right?
Yes.
Yeah, so this definition is not useful for robot arms, I don't think, is my opinion. It is useful to say that, what do you call them? Cutting tools, automated cutting tools are not robots. That is where it is useful. Any other opinions, questions? Okay, so another definition is, robotics is a science of making robots. So we go completely, outside of defining what robotics is. We instead define what a robot is. Okay, so this is a trick. Instead of trying to say what constitutes the science of robotics, we just say whatever, making robots. And robots, presumably, would be easier to define. And the robots include stuff like industrial arms, quadrotors, automatic vacuum cleaners, walking robots, underwater robots, etc. But it does not include washing machines, airplanes, rockets, cutting tools, 3D printers, etc. You can see that it is completely arbitrary, right? Like, how is airplane and not a robot? Like, what makes airplane not a robot? Because there's a pilot in there? Well, what if you consider airplane without a pilot? We have those, like spy planes, I think, are usually without pilots, high altitude ones. I don't know, I didn't study those kind of technology, but I presume there are plenty of airplanes without pilots. And even the airplanes with pilots only do work during landing and takeoff, and they speak on, with the ground. That is their job. So most of the time it is cruise control that does the work. So how is airplane not a robot? It has actuators. It takes information about the environment, and very complex information too, like weather, like the wind speed, etc. GPS signals, and it corrects, multiple motors, and especially the engines, and somehow, and even corrects like those airfoils. At least it can, right? Somehow this is not a robot. While vacuum cleaner, which is extremely primitive, at least the first iteration of vacuum cleaners were extremely primitive. That is a robot. I don't know, maybe one of you can tell me why, what makes a cutoff? But yeah, in my opinion, this is arbitrary. Here you can ask yourself, is autonomous cars, are they robots or not? Like, do they count? Because if airplane doesn't count, autonomous cars is just the same. It can have a pilot, but it doesn't have to, right? We hope that autonomous cars eventually will operate without pilots. But at the moment, they usually have a safety pilot. So the situation is one-to-one with airplanes, right? But and some people would say autonomous cars are not robots. There are plenty of people who would say that they're not robots. So it's interesting, right? It's pretty interesting. I personally don't have an opinion about that. All right. So the way I propose for us, I mean, this is all like not something you need to memorize. It is just kind of like for your information, since you're going to think about it, again and again. So I want you to have a framework to think about it. So the way I propose to use the term robotics or what is a robot, etc., is trying to use it when it is useful. Like when you know that calling something a robot is useful for the discussion, it explains what you're trying to say, it conveys information, then you can use the term. If on the other hand, calling something a robot makes it more confusing, if saying that this is the robotics again makes it less easy to understand what you're trying to say, then don't use it. That is my proposition. And you would soon find that there are ways in which people use the terms, and you can just use it in a similar fashion. Sometimes going outside the borders is exactly what you want to do. Human communication is based on metaphors and allegories, etc. But just as a framework to what is robotics, you can use the term when you think it describes something well enough. Like, for example, if someone asks you what you're studying, you can say, I'm studying robotics. That actually explains what you're doing really well, right? So, all right. That is just about the terminology. Okay. If you have any questions, we can answer them. But I understand that this is not a this is not a technical topic. So, okay. While I kind of presented robotics as this nebulous thing where we don't even agree on definitions, and this maybe is starting to worry you, like what are we going to study if we cannot even agree what robotics is? While that is true, there are some aspects of robotics that everyone expects you to know, okay? Kind of like background information that you have to know. Background information includes kinematics and dynamics of serial robots. What is a serial robot? Well, robot arm is a serial robot because it has links which connect one to the next, to the next, to the next, as opposed to parallel robots which connect like in rather than being like a tree, they're kind of like a net. I don't know if I explained correctly, but robot arm, you can imagine, it has one link. Let's say one link, right? Then it has a joint, another link, another joint, another link, right? Serial. So it connects in series. Okay. Parallel robots, on the other hand, imagine if you have like two links connected to the ground, like one link here, they're connected to the ground. You have two joints, one joint, another joint, one joint here, say another joint here, right? They're not connected in series. You cannot say we go from this link to this link to this link to this link to this link, and because if you have like three links connected to each other in one place, like one link, another link, another link, you won't be able to count from one to the end in some natural fashion. So basically they can, parallel mechanisms. We'll maybe look into examples a little bit later, but those are different, and understanding them is not a core part of robotics. Series mechanisms are though serial linkages. You have to understand them. Somehow this is assumed that you know if you study robotics. Okay, you are also assumed to know a little bit about single rigid bodies. So single rigid body dynamic and maybe a little bit kinematics. We're talking here about drones, underwater robots, cars, delivery robots. All of those are single rigid bodies. Well, in this lecture, we'll actually look into this in a bit, but you understand what I mean, right? It's just one object that doesn't have any joints, any link, connections to anything. So those things, drones, underwater robots, cars, delivery robots, are well described by the word, by serial rigid bodies. All right, and combination of the two, that is walking robots, mobile manipulators. So sometimes you have a need to understand both SRB, single rigid body, and a serial linkage. So those things are part of the core concept of robotics. There are other core concepts, but we're not going to get through all of them. Like not today, not even throughout the whole course. For example, PID controllers are also a core concept for robotics. And stabilization, feedback control, those are also core concepts. But you don't have to learn them in this course. There'll be other courses. And if you studied control theory, you already saw PD control, so proportional derivative control, which is what the feedback control that you saw in state space. That is PD control if you go from a mechanical equation to a state space equation. So PID control is just one more, there is one more component there. All right, so also sensors, there are quite a few sensors that you kind of have to understand. Again, you would have a separate course where you would learn about those. So we're not trying to cover all prerequisites, but some of them, especially the ones that I mentioned here, we have to cover them here. You have to know them before you move on. All right, so that is what this course is about. So while robotics, as I said, is ill-defined, what we want from this course is well-defined. So don't worry about that. All right, let me give you more explicitly the list of things that we want to understand after studying this course. So first, we want to understand forward kinematics. This might be something that you already saw a little bit in theoretical mechanics. Maybe you actually studied it well in theoretical mechanics, I don't know. But I'm sure that the methods and terminology in this course would be quite different. So I don't expect that you would be bored. You'll probably be fine. Frame transformations, that I'm almost sure you never studied. Jacobians you probably heard the word from multivariable calculus. But here I would explain how they're useful. Null spaces is quite a useful idea, especially for Jacobians. That is part of analysis that you're going to do. Relations between forces and joint torques, between Cartesian and joint velocities. All of those have again to do with Jacobians. And those are very simple things once you learn them. And learning them is not so hard. So that is something that you will appreciate when you study. It will give you a lot of ability to do real world stuff at the very little cost in terms of understanding. So that's a good topics. Inverse kinematics, that's again, you don't study it anywhere else, in our courses, it is pretty much only in introduction to robotics courses. Dynamics, that you studied quite a bit in theoretical mechanics. Here, though, we'll concentrate on specific types of dynamics and how to derive it, etc. So there will be different and new information. Trajectory planning, we are only going to get a little bit of that. On the practical sessions, you will see traditional trajectory planning with robot arms, which is industry standard, extremely useful. On lectures, you will see a little bit of modern field, like the way we do trajectory planning in, challenging modern scientific applications. I will give you introductory level stuff here, but this is pretty much, a whole course could be on that, and even such a course would be still fast-paced. Is a very big field. All right, and all of those are directly useful for industrial robotics, but some of them are actually useful for example, for computer vision. Frame transformations constantly used whenever you work with cameras, because you need to understand from which direction and where the camera is placed to see what's the information you're getting. Trajectory planning is the core of all autonomous robots, like cars, rockets, airplanes, everything. So those things would be beneficial for you even if you are not working as a roboticist. If some of you are going to work in computer vision, this will help you. If some of you are going to work as a SpaceX engineer, this will work for you. Okay. All right. I think is enough introduction. I'm always wary about making long introductions like this because, there is only so much motivation to listen to abstract stuff. We are engineers. We want to listen to concrete things, right? Is there any questions about what we discussed here? Because I am going to move on to definitions and core content. All right, no questions. Okay, so first, before we start with the serial robots, let us remember some terminology from classical mechanics. Let us remember some terminology. So first, a point mass. A point mass, you can think about it as just like a tiny, tiny thing which has a mass, right? It is an object which is characterized by its position, okay, in 3 dimensions, and its velocity in 3 dimensions, and a mass is a scale object. By the way, do you understand the notation that I use here? For example, like this thing. Is it clear what it says?
Yep.
No one has. Okay, good. If I introduce some notation which is not clear, please stop me and ask a question. If it is not clear for you, it's probably not clear for other people as well. Yeah, so please just stop me and ask what is that. So point mass has only those 3 characteristics, unless I forgot something, but I think I didn't in this case. So it has a position, current position somewhere in space, current velocity, okay, and a mass. So can someone tell me why acceleration is not here? Why did I mention position, velocity, but I did not mention acceleration? Can someone tell me?
It is not characteristics of an object. It is characteristics of objects interaction.
Yeah, that is a very good. That's a very good answer. So in a sense, velocity would be, acceleration would be dependent on forces outside of the object, right? We are not going to consider like propulsion and etc. But yeah, those also can be described as interaction with outside objects, of course. Yeah, indeed. And I think another way to think about it is this: none of those characteristics, like position, velocity, and mass, can change instantaneously. Okay, none of them can change instantaneously. They can change, but they will change smoothly. Okay, so there will be gradual change in position, in velocity. Mass usually stays the same. So things which cannot change instantly are usually what characterizes an object. Okay. So later, if when we study control, you'll notice that control can change instantaneously, like control input, even if it is the internal control input for the robot. Like robot can instantaneously change it, the torques applied to it. And this is oversimplification. In real life, of course, it is not instantaneous, but in our models, it is. And therefore, torque does not characterize an object. State of the object cannot change instantaneously. So state characterizes an object. All right, but in this case, indeed, those are the 3 that do it. Okay, good. So let's consider an example. So if you want to model a satellite orbiting a planet, it makes sense to describe its position and velocity. And it makes sense to consider its mass. By the way, if you only care about where the satellite will be in the next moment of time, you don't need its mass. Satellites, as long as you know their current position, current velocity, they're completely described. So mass does not play a role there. But if you want to know how much propulsion or external forces or something else will influence the change in its velocity, then you need the mass. So you can see for a satellite, it might be useful to know its mass and to know its position velocity. Okay. Next, a rigid body is an object that is characterized by its position, again, R in R3, orientation, T in SO3. I will go back to what SO3 is in a moment. Velocity of the center of mass, again, R3. Angular velocity, again, R3. Mass, scalar, as before, and inertia, which is a 3x3 matrix. Okay. Have any of you already encountered the word SO3 before? So no one have seen it before, right? So let me explain. So SO3 is like normally in a reasonable world. You wouldn't have to learn this notation, but we live in a reality which is, ours, and there you have this notation in the introductory course to robotics. That is a little bit scary, but yeah. What this says is that T is an element of a group of rotations. Group of rotations, the word group here refers to the group theory. Group theory is, you can think about it as the most advanced type of algebra. That is probably completely incorrect, but you can think about it this way. Most advanced form of algebra, where you go beyond considering, like matrix vector multiplication, matrix multiplication, etc. And you consider abstract objects with abstract operations on them. In group theory, you can form, groups which have certain properties that are useful to study. And like our linear algebra stuff that we do is kind of like one of the offshoots, you can say, of a group theory. Of course, historically, it was algebra that was first. Group theory kind of comes much later to explain stuff. But so you can think of it as much more abstract. And it doesn't have to work with just linear objects. It works with nonlinear objects as well. Like you can do group theory on exponentials. You can do it on, use it with differential equations. And one particular aspect is rotations. Like rotations in the real world, where you have something and you want to rotate it, right? Those rotations are well described by elements of a group of rotations, right? And I don't mean now like necessarily like purely mathematical objects. You can imagine like a real world rotation. Again, you have an object and you want to rotate it to a different orientation. This operation is well described as an element of the group. However, I said all of this about the group theory, just so you know where the word comes from. We're not going to study group theory, even an introduction to it. We'll take a couple lectures. We don't have the time. But if you on your own would like to look into group theory, I think it would be beneficial for you. Somehow helps you understand both algebra and some aspects of robotics better. But we're not going to. We're not going to study it in this course. Now, the reason why roboticists write it this way is because it is hard to write it in some other way, okay? So how would you describe orientation of a rigid body? Let's say you have a rigid body and you want to describe its orientation. How would you describe it? Give me some suggestions.
There are several types of Euler angles we can use to describe.
All right, Euler angles, sounds good. How many angles do you need to describe the orientation of a single rigid body?
3 angles.
3 angles. Okay, good. That sounds great. You know that, by the way, I'm reading the chat, so I notice responses from everyone. Konstantin, Anton, etc. So thank you. Thank you for responding in the chat too. Okay, 3 angles. You know that there is this thing called, how do they call it in English? Log?
Singularity.
Yeah, singularity, right? There is a specific name for the singularity according to Euler angles. I think Cardan log, something like this. But anyway, singularity, right? So there is this one orientation where you cannot recover exact values of Euler angles from this orientation. you can recover like 2 numbers, but you need 3, as in 2 of them become kind of like independent. That would be easier enough as a picture, but maybe we would look at it later. But yeah, you are aware, right? There is singularity. Euler angles.
So to overcome singularity, we can use quaternions.
Quaternions. Great.
Yeah, quaternions.
I'm glad that you know quaternions. So quaternions, how many parameters quaternions have?
As I remember, 4.
4, right? 4 parameters. Exactly. Great. That is what I wanted to hear. 4 parameters. They are dependent. So the norm of a quaternion has to be equal to 1. But 4 numbers, right? Okay. Did anyone, any one of you studied rotation matrices? Rotation matrices.
I believe we all did in some way.
All right. So rotation matrix, how many parameters does it have?
You mean rotation matrix about some axis?
Yeah, in 3D. In 3D.
But in 3D, rotation matrix is just 3 by 3. So
Yeah. So how many parameters?
okay, so 9 parameters.
9 parameters. Exactly. 9 parameters. Great. 9 parameters. So you see what happens, right? Euler angles, 3 parameters. Quaternions, 4 parameters. Rotation matrix, 9 parameters. So we cannot use R3 or R4 or R9. It won't make a lot of sense because it would describe specific quaternions, Euler angles, or rotation matrices. And we don't want to specify the way orientation is described. Maybe I will describe it with Euler and you will use quaternions. Who knows? So it doesn't make any sense to impose this on your reader, right? That is one reason to say SO3. And everyone knows in robotics what SO3 is. So instead of saying orientation is R3, meaning Euler angles, or R4, meaning quaternions, we say orientation is SO3, and you parameterize it the way you want. You have to remember, though, that in actual code, it is always parameterized somehow. You cannot have like completely like no parameters to describe orientation. So SO3 is a useful indicator of orientation as a thing, right? But it does not tell you how you parameterize it, and you have to parameterize it. Okay. Another interesting reason why people say SO3, and right now I'm going to say something complicated, so don't worry if this is a little bit too much. It's okay. I'm just going to explain how it is, but we'll maybe come back to it later. So another reason is there are no perfect descriptions. For example, Euler angles have a singularity, so it automatically makes them unusable for some applications. Maybe somewhere in dynamics equations, maybe somewhere in trajectory planning, but they stop being useful. Okay, in some way. Quaternions are excessive. You have 4 coordinates, but only 3 of them are independent. There is something, I believe it's called like two-leaf covering. Basically, it's I believe that is like not my area of expertise by any means, so don't take it too seriously. But I believe there are 2 quaternions that can be used to recover any given orientation, I think. But the point is they're excessive. So if you're going to derive dynamics equations with quaternions, you would have a little bit of extra trouble. Like with Euler angles, you don't have a lot of extra trouble. You just derive it normally. With quaternions, you do. You would have extra trouble. Okay. All right. And with rotation matrices, out of 9 parameters, only 3 are independent. So the amount of extra trouble there is just enormous. And then probably people do derive dynamics equations with rotation matrices, but I haven't seen it. So what I'm trying to say is, like, no matter what you pick, there will be downsides. And right now, some people even try to work directly on groups rather than working with parameterizations, and try to take Jacobians with respect to group operations. So I'm not going to go into details, but you know, maybe if you want, somewhere in the class we'll have a more discussion about rotations, and then I will share those things. But yeah, basically what I'm trying to say is, fundamentally, SO3 is a correct way to describe rotations. It is not that roboticists want to, you know, show off how they know group theory. Somehow, very deep inside, this rotation has to be described this way. So that is the point. Right. Sorry if it was too long an explanation, but now you hopefully understand why SO3 and not like R3. Okay. Velocity is R3 as before, so no surprise here. Angular velocity is also R3. So we were talking this whole time about how rotations are not R3, but angular velocity is R. So angular velocity is R, just that, three-dimensional vectors. You can think about velocity, angular velocity, as somehow describing a axis of rotation and how fast the body rotates around it. Or you can think about it as just a parameter. Yeah, so angular velocity. And notice angular velocity is not a derivative of Euler angles. You probably have seen it before, but I don't know, maybe you didn't. But Euler angles, they have their time derivatives. Angular velocity is not a time derivative of Euler angles. The relations between time derivative of Euler angles and angular velocity is called Euler kinematics equation, Euler kinematic equations. It probably doesn't help that everything is named after Euler, but yeah, derivative of Euler angles and the relations with angular velocity is called Euler kinematics equations. Yeah, but you don't have to memorize it. Basically, if you're going to do like you know, serious robotics on rigid bodies, what you have to do is look into tables where they describe to you relations between various derivatives, etc. Or like, you know, Euler angles to quaternions, how to transform. Derivative of Euler angles, derivative of quaternions, how to transform. There will be tables like this, you can look it up. So don't worry about it too much. Right, by the way, I think I'm being a little bit slow with the lecture, so I will try to pick up the speed a little bit. Don't want to make the next class start late. All right, last thing is inertia. Inertia is a 3x3 matrix, but yeah, but I think only 6 parameters are independent. So here, if I wanted to be like very precise, I would have said something like it is a member of symmetric matrices group or something like this. But here we don't have to overcomplicate it, because inertia always, as far as I know, always described by 3x3 matrix, symmetric, and yeah, 3x3 matrix and symmetric. You can look up how to compute inertia matrix, like elements of the diagonal have to do with like in moments of inertia next to axis, etc. There are ways to compute it. But you know, in our applications, we'll most likely not compute it. That's why we're not going to spend time on it. It is possible to compute it by hand, is what I'm trying to say. And usually CAD software, computer-aided design, like SolidWorks or AutoCAD, they will be able to tell you in moments of inertia of rigid bodies that you design there. All right, now example. Things that are modeled like rigid bodies is, for example, drones. For it, it's not enough to describe position and its position. You also need orientation, because you can imagine if it is a quadrotor and wants to like turn around, you want to know how its orientation is, because it has motors here, here, and here. If you give it command in this position to turn around, it will turn like this, fly in this direction. If it was orientated this way, you could tell it to turn around and flies in this direction, right? So you have to know its orientation. That is a difference. Please notice that both satellite in the previous example, the satellite, and drone, they both have orientations. It's not like one of them doesn't. It is just that for drone, it is very important to know its orientation. It is hard to make a useful model of a drone that does not take into account its orientation. All right. Also, it is good not only to know its mass, but also its moment of inertia. Moment of inertia, you need it to understand how quickly it can turn around its axis. All right. Now, we have another quite complex thing to cover, that is joints. Did you study joints in theoretical mechanics? Any of you?
I think we covered some basics and types of joints and limitations that they give for specific mechanisms.
Oh, so you did study it. Okay. So well, all right. I will try to explain joints, here. Let's make sure that after I explain it, it is clear. So if for someone it is not clear, please stop me and ask a question. Okay, because like we will use this for the rest of the course. Okay, so a joint is somehow a constraint, right? That is placed on a rigid body and it restricts its movements. Okay, so the joint that we are going to use the whole time, pretty much one joint, is a pin joint, or you can call it a revolute joint. The way to describe it is kind of like, imagine this as a hinge, right? What a rigid body allows is to rotate one rigid body relative to another rigid body, okay, or to the ground. It doesn't allow any other motion. So you cannot do anything but this rotation. So there's this axis, right? Axis. And you cannot do anything but rotate around this axis. Okay? So you have to, somehow you have 1 degree of freedom, one rotation. Okay, so door hinge is a good example of a joint. All right, motor, like a typical DC motor, is also a good example of a joint or pin joint. So they allow only one rotation, right? One rotation. There is nothing else around the axis. Okay. Here is an example on the figure 1 of how the pin joint looks. And here are all the notations that people come up with to depict it graphically. So you can see here there's a joint, there's a original body, another body. You can see the angle that they have between each other. This is the way people describe joints. This is the way you can see original body, new body, and this cylinder is a pin joint. Cylinder is a very typical description of a pin joint. So here, what you have is again description of a pin joint, and here is again description of a pin joint. I think this pictorially is clear enough. This two. All right, so pin joint, that's what we're going to study. Other types of joints include, like this is again pin joints, those two. This is a prismatic joint, so it goes forward and backwards. like if you have a drawer where you can kind of draw your полочка по-русски. That is pin joints. Like you can go back and forth. Okay. This is universal joint. It has 2 rotations. You can think about it as a pin joint, but with 2 rotations. It has this very specific design with a cross shape here. It allows 2 rotations. I don't think it is used very often right now, but it can be used. We also sometimes, I believe, call it cardan joint. This is a spherical joint. Spherical joint is kind of like your shoulder. It can rotate like, like this, like this, like this. So it allows you 3 rotations. No translation though. There are other types, but I think is enough. This is enough. We're not going to use them very often. We're going to mostly study pin joint. Questions? No questions so far, right? Okay. So industrial robots, walking robots, they mostly use revolute joints. There is a big exception of orthogonal robots, like 3D printers. What they use is, it's a little bit depends on how you describe it. You can describe it as using prismatic joints, or you can describe it as using screw joints. No matter how you describe it, they basically go forward, backwards, upwards, downwards, etc. Orthogonal, usually parallel robots, they use those things. All right, but what we will study in this course can apply to all those joints. Just because we don't study prismatic joints explicitly doesn't make it not applicable. I mean, just trust me. You study this course. Afterwards, if you encounter a different type of joints, you'll figure out how to use the material with this different type of joints. So don't worry. All right. Now, a rigid body, which is attached to something, let's say, for example, to the ground, via a joint, is called link. Link is you can think about it as a body attached to something else, right? Link, which is attached via pin joint, is characterized by its orientation, which in this case, please notice, is a one parameter, single parameter, Q in R. So there's just one parameter that requires to describe the orientation. Notice it is a rigid body still, but only one parameter is required to describe its orientation, because pin joint makes it sufficient. You still need its velocity, but it is also a single parameter. Mass is as usual, and moment of inertia, I keep it as 3x3 matrix. Why? Because just because the link is attached to something else doesn't mean that the whole mechanism is not going to move around. So you still need inertia, like the complete inertia of the body, to be able to describe the whole linkage, right? But if it was completely the case, just one link attached to the ground, then you could use a single inertia parameter here, moment of inertia around the axis. For example, a pendulum is a good example of a link, right? You studied pendulums, right? Those things that go back and forth like this. They're described by angular velocity, both scalars, a mass of the pendulum, and the moment of inertia of the pendulum. So that's how you describe them. Questions so far? All right. So let's consider the pendulum a little bit closer. So here's a picture of a pendulum. Here's the angle between the vertical axis and the shaft of the pendulum. This is a hinge or the pin joint. Here's a what we'll call end effector. So the end of the pendulum in this case. All right, so that is it. So the pendulum can be described by angle phi between the link and the vertical line. And the length of the pendulum, we will assume it is L, right? As I said, this is at the end of the pendulum. Okay. Now, with that, we can find the position of point RK. So we can find position of this point. How? Well, just using normal kinematics. So we know that RK is equal to L times sine of phi, L times, and that is its x coordinate. So this coordinate here is L times sine phi, and this coordinate here is L times cosine phi, with a minus sign in this case. We can differentiate this position with respect to find velocity. You remember derivative of a sine is cosine, but phi is also a function. So that's why when we differentiate this equation, we get phi dot times cosine phi, and L, we're not forgetting it. Derivative of a cosine is minus sine. So that's why minus it disappears here. Okay, so this is a derivative of k. So derivative of RK is a velocity of this point, and you can imagine its velocity will point somehow this way, right? So it makes sense that it is positive. It points towards the first quadrant. So here, like it's positive this way, positive this way. All right. So far easy, right? Nothing too difficult here. No? All right, good. So this so far is just description of a pendulum. We found the position and velocity of this endpoint of the pendulum. Okay. Notice that we could also do it with rotation matrices. We can say that RK is equal to some, the position of RK when phi is equal to 0, which is 0 minus L. Why it is 0 minus L? Well, let's look here. If the let me find something. If RK was here, what would be the position of RK? Well, x would be equal to 0, y would be equal to minus L, right? So that's fine. Okay, now so we get this initial position, and we can multiply it by rotation matrix. This is a rotation matrix in R2. Those rotation matrices are a little bit simpler, right? So we have this situation. So we have our vector, we multiply it by rotation matrix, and we get indeed what we expected, the same result. We get the position of RK. Is this clear? And the sense that this might be a little bit kind of like, mathematics is clear, but cannot connect with it. That is fine. We'll connect with it sooner or later. But I hope at least mathematics is clear here. Okay. Now consider double pendulum. Double pendulum. We're going into a difficult territory. So again, those are pin joints. Pin joints. Those are angles that describe rotation. Okay. Here is the position of a first pin joint, the position of the second pin joint. This is a end effector. RK is an end effector. 1 second. Oh, okay. Thank you, Ivan. Okay, so those are positions of joints, those are angles, and this is the end effector. Okay, good. Now we want to find position of compute the position of end effector. Well, as before, we can say it is the length of the first link is L1, the second link is L2. So we get L1 sine Q1 plus L2 sine Q1 plus Q2. Why is this summation here? Well, because the angle is defined as relative to this angle, right? So the absolute orientation of the second link is the sum of Q1 and Q2. Q2 only describes how second link is oriented next compared to the first link. Okay, so this is the position of the end effector. Now let us take its derivative. So the velocity of the end effector can be found by differentiation. Notice differentiation is quite simple here, right? Hope I didn't mess up anything. Let me just double check. Did I? All right, anyway. Notice that here Q1 plus Q2 is Q1 plus Q2 gets in front of the brackets. So it is derivative of a composite function. So first you take derivative of the original function, then multiply it by derivative of the parameter, so of the input to the original function. So first take derivative of the cosine, then derivative of Q1 plus Q2, and that is Q1 dot plus Q2 dot. Same here. Now, if we used different angles, like let's say we say phi1 is equal to Q1, and phi2 is equal to Q1 plus Q2. So those would be absolute angles. So they would describe position of each body relative to the ground or relative to the vertical axis in this case. Then position of the end effector would be described in just this way: L1 sine phi1 plus L2 sine phi2, L1 cosine phi1 plus L2 cosine phi2. Right. Except I think there's minus sign missing here, and that's why here is the extra minus sign. I think that is a mistake I was looking for. There should be minus signs here. All right. And then you would have derivative of this function here. And the derivative you can see is kind of the same, but you have phi dot going from under the sign here, phi2 dot going from under the sign here, right? And you note that it is quite easy to go back and forth between those notations, like knowing what phi2 dot is. Like knowing this expression, you can easily substitute and get to this expression. Basically, going between 4 and 6 is easy, right? But also note that the form of forward kinematics depends on what kind of angles we use. If it is joint angles, so relative angles, Q1, Q2, there will be one form. If it is absolute angles, there will be like phi1, phi2. It will be a different form. You need to keep in mind that there are two forms, and they will give you different results. That's just that is the important message here. Different angles will give you different results. Questions so far? Okay. Now we can still express these kinematics as via rotation matrices. So we can introduce a rotation matrix here. right? Yeah, we can introduce a rotation matrix here. There shouldn't be minus sign here. There should be, right? There should. Yeah, now this is correct. Now it's correct, I think. Yeah, let me just check. Okay. So we can introduce this rotation matrix here, and this will rotate the first joint, right? And then we can introduce this rotation matrix here, and this would rotate the second joint. The first rotation depends on one angle, relative angle. Second rotation depends on two angles, right? Because the first joint is only rotated by Q1. Second joint is rotated by Q1 and Q2. Okay. So, yeah. All right. This is a mess. All right, we'll fix the slide after this lecture. Now, this rotation matrix can be represented as a product of two rotation matrices. Can be represented as a product of rotation matrix around with the first angle and rotation matrix with the second angle. So if you multiply them together, you get this rotation matrix, and that is important part here. So if you have two sequential rotations, you can combine them into one rotation matrix. The sequence of rotations is important. For rotations in R2, sequence is not very important. We can probably prove it, that we can change the sequence of rotations, nothing will change. But in R3, sequence of rotations is important. And we'll see it soon. So, but the message is, if you know the sequence of rotations, you can multiply those rotation matrices, and you can get one single rotation matrix. That is part of what it makes it a group, right? You can do a group operation on an element of a group, and it will give you another element of a group. So, all right. So all I wanted to say is that this rotation matrix comes from this multiplication. And here, obviously, we have error. This doesn't need to be here. All right. Now, last detail. Let's say we want to compute angular velocity of a rigid body. Angular velocity is a rate of change of orientation of the rigid body. The rate of change of orientation. That sounds interesting. And in a sense, you see, I'm referring to orientation itself, not parameters of the orientation. So it's not a rate of change of some angle, it's a rate of change of orientation itself. Okay. So orientation of the first link is given as Q1. Orientation of the second link is given as Q1 plus Q2. The rate of change of the orientation can be, in this case, found by differentiating. So we can find angular velocity of the first link as Q1 dot, of the second link as Q1 dot plus Q2 dot. All right. That was this simple because those angles directly represent orientation, like orientation of Q1 of the first body is Q1, second body is Q1 plus Q2. In 3D, we will find that it is not so simple. But that is in 2 lectures, I think. Okay. I think this probably looks trivial enough, so it probably doesn't scare you. All right. I think that is it for the introduction. Now, just a little bit, housekeeping. So first of all, the lectures will be available on the GIP page here, Fundamentals of Robotics. You can get to the page just clicking the link or scanning this QR code. I will keep it on the page so you have time to scan it. Of course, I will send the link to the chat. What is going to happen on the Git page? On the Git page, we'll have, let's see if we can move there. The Git page will have all the slides. You will be able to click, here you get the slides. They'll be in LaTeX. So if you need to use some formula or whatever, you can copy it from there. If you want to fix an error, you can make pull request, much appreciated. Here I would put links to the videos, lecture recordings. And here are book suggestions. So for this course, we suggest Robotics, Modeling, Planning, and Control by Siciliano and co-authors, and Robot Dynamics and Control by Spong and co-authors. So those are classical books. So it is probably good for you to see them. You don't have to read all of them. It's just, if you want to reference something, it's good. But in general, all materials that I'm going to ask you to remember, learn, and that I will going to, use on exams and midterm are contained in the lectures. So I'm going to try very hard not to have anything that is not in the lectures to be in any of those types of things like in midterm or exam, right? You'll have homeworks. You probably in next class, Alberto will explain to you what homeworks will be like. But yeah, like gradable assignments, I would call them. All right, but yeah, so this Git page would have all the information. We're going to try to upload it to Moodle fast too, but I would prefer it if you use Git page. The reason is if I fix an error, it is immediately fixed in the Git page, right? And but on the Moodle, it will have to re-upload the PDF, etc. It might take time. Lecture videos will also be all updated here. So like practice just shows me it is easier to navigate using Git. All right, that is it from me. If there are any questions.
Can you clarify the structure of the course? I mean, how many assignments will you have? Will we have, you said, midterm and final?
Yep. Yeah, we will have midterm and final. I believe we have 3 assignments. Maybe Albert can tell us, do you have this, what do you call it? This structure with percentages somewhere near you? Maybe you can tell us how we do it.
Yeah, but I'm not with the laptop right now.
Okay.
I'm not connecting with laptop right now.
Okay.
But
No,
yeah,
fine.
we will have around 4 assignments, each of them for 10%. One of them is practical, which we will start preparing this week. But we will get this assignment probably on Wednesday. There will be 3 other assignments based on the theoretical part from the lectures, and of course with the practice in the labs, how to solve problems mathematically. So 3 theoretical assignments and 1 practical assignment plus exams.
So 4 assignments, exam and midterm, right?
Yeah, so exams and midterm and final, they both count for 60%, and 4 assignments count for 48%.
Thank you, Albert. Right, but we'll post all this information somewhere this week. And yeah, there will be topics, assignments, percentages, etc. Sorry for not posting it right now. Maybe next class we'll start with going over all this information. Thank you for the question. Any other questions?
So, Professor, thank you for the lecture. I just want to emphasize, first of all, that just in case all our group is Russian-speaking students,
Mhm.
everyone. Yes. Second of all, we already have some information about the course in the Moodle.
Mhm.
So I believe it is irrelevant because it says that we would not have a midterm. So could you clarify on that?
We'll
Yeah.
update Moodle. We'll update Moodle.
Okay.
Yeah,
Thank you.
these topics are just like hidden, all these topics now, because it looks like it was a mistake from last semester that they stayed visible and they should be automatically hidden. But I fixed this now. You'll find Moodle is nearly empty, and we will update it with the new information. I just fixed this problem right now.
Yep, we'll fix Moodle. Apologize for that. Any other questions? Oh, we have something in the chat. Yeah, so Moodle we will update. Yep. Any other questions? Yeah, I understand, by the way, that everyone here speaks Russian, but I think if we teach you in English medium, it would also be beneficial. Not because somehow it is better intrinsically or something, but because the terminology of modern robotics is just not reflected well in Russian language. As in, it is well established in English. It's not as clear, at least for me, established in Russian. And once you learn the international terminology, you'll be able to go back to understand Russian terminology, no problem. Like we have seen it plenty of times, so that is not a problem. But if I need to explain something in Russian, I would be open to it any moment. So, all right. Is there any other questions? Okay. Thank you everyone for coming, and I apologize for whatever technical and other problems we had. We will see each other on the next lecture. Goodbye.
Thank you for the lecture. Goodbye.
Bye.